flying windmill, egg beater. By any name you choose to call it, the helicopter is whirling its way to eminence as one of the most important developments in the history of man-made flight. A comparative newcomer to the aviation scene, the helicopter actually embodies flight principles that have been studied for centuries. Rotating and flapping wings, many of them in imitation of the birds, were being designed in the early 1300s. In the 15th century, the great artist-inventor Leonardo da Vinci made several sketches of an aircraft-like machine with lifting screws rotating about a vertical axis. But for 3 centuries afterward, interest in rotary wing flight was virtually non-existent. No effective means of supplying continuous power had been devised. In the early 1900s, the Frenchmen Cornu and Breguet and Russian-born Igor Sikorsky were making their initial but inconclusive experiments with early gasoline engines to turn the rotors. Not until 1937 did interest in the helicopter revive, when suddenly out of Germany came dramatic news of the remarkable Fokker helicopter, whose performance was reported to be vastly greater than anything achieved so far. In that year, Hanna Rösch, famous German woman flyer, flew the first experimental machine from Bremen to Berlin at an average speed of 68 miles per hour, and took a subsequent model up to 11,700 feet. By 1939, Sikorsky, now in America, had built his famous VS-300 machine, the first to find a good solution to the hampering problem of torque reaction. From this time on, the helicopter played an increasingly important part in peacetime and wartime aviation. Compared with the advance in fixed wing flying, helicopter development until recently has been slight. Most designers have centered their attention on altitude and speed. But as Sikorsky himself pointed out, mastery of the air will depend not alone on how fast we travel, but on how far we stretch the difference between high speed and low speed. How far supersonic planes will stretch this difference in one direction, we can only guess. But the helicopter has taken us to the very limits of the other extreme. The helicopter can stand still in midair. The helicopter can take off vertically. It can move forward, backward, or sideways. It can travel 100 miles an hour or a few feet an hour. It can land with or without engine power on a few feet of landing surface. The combination of these qualities make possible a whole new field of air operation. The helicopter is excellent for reconnaissance and liaison work, for spotting missions and supplying troops in the field, for transporting equipment and personnel between points otherwise inaccessible by air, for rescue work, as proved by its heroic service record in Korea. To begin our study of rotary wing flight, let us first examine the basic principles of aerodynamics which enable the helicopter, or any craft for that matter, to support itself in airborne flight. When a conventional airfoil, like an airplane wing, is passed through the air mass, the air separates in front of the airfoil's leading edge and slips around it much as water slips around the sides of a moving ship. Now, let us vary the angle of attack, or the angle at which the airfoil passes through the air mass. We tilt the wing upward slightly, and the stream of air passing over the top of the wing is unable to hug the surface as closely as does the air striking the wing's bottom surface. This creates a low pressure along the top surface of the wing and a high pressure on its undersurface. The result is lift to the airfoil. In a helicopter, however, the airfoil is not a fixed wing, but a series of 2 or more wing-like blades which revolve around a hub. When pitched at an angle of attack, the blades create this same low pressure along their top surfaces and high pressure against their lower surfaces. The result, as with a fixed wing, is lift. On a fixed-wing aircraft, the angle of the airfoil's attack depends entirely on the attitude or position of the aircraft itself. In the helicopter, however, the angle of the blade's attack may be altered independently of the fuselage. Recognizing that moving an airfoil through an air mass gives an aircraft the support it needs to become airborne, let us see how the helicopter utilizes this principle. The primary forces to produce flight can be classified as thrust and lift, which must be produced in greater force than drag and weight in order for flight to result. In fixed-wing craft, thrust is supplied by the engine-propeller combination or jet thrust. Lift is supplied by the wing surfaces. In the helicopter, however, thrust and lift are supplied simultaneously by the main rotor, which is driven by the engine. Now that we've discussed the principles producing flight, let's see how the helicopter is controlled in flight. Controlled flight is the coordination of vertical flight, horizontal flight, and steering. Vertical flight is achieved by the turning of the main rotor blades, which are powered by a gasoline engine. The engine is situated in the fuselage, which also houses the pilot and necessary controls. Now, if the speed of rotation and pitch of the main rotor blades is sufficient, the plane will rise. From this it follows that varying degrees of pitch will produce varying degrees of lift. A greater degree of pitch with sufficient engine power to maintain rotor RPM will naturally produce a greater rate of climb. Lesser degrees of pitch will produce less lift and thus enable the machine to hover or descend. To produce these varying degrees of pitch, we employ a control system known as collective pitch control. A collective pitch stick, situated to the left of the pilot's seat, connects to the rotor blades by a series of linkages and bell cranks, and moves the blades on their pitch bearings. To raise our machine, we increase the pitch by pulling up on the collective stick. But immediately, a new problem arises. As the blades increase their pitch, they naturally offer more of their surface in passing through the air mass, thus creating greater resistance or drag. The tendency would be for the blades to slow down. So to keep our blades turning at the necessary RPM, we must draw more power from the engine. We do this by turning the motorcycle-type throttle built as a handle on the collective stick. In most helicopters, the movement of the stick and the compensating movement of the throttle are synchronized. But even so, the pilot must make small adjustments frequently. Assuming then that our machine is rising from the ground, we encounter still another problem. A phenomenon takes place called torque reaction. Torque reaction is the tendency of any force applied in a specific direction to create an equal force in the opposite direction. In this case, the engine is producing force to drive the blades in one direction, but an equal force tends to swing the engine itself around in the opposite direction. Since the engine is not anchored to any stationary object, but instead is held inside the free-swinging fuselage, the fuselage of the entire helicopter tends to spin around in the opposite direction to the blade's rotation. Controlled flight under this condition would be impossible. Sikorsky is credited with being first to produce a practical answer to this problem. As a result of his experiments, we now use a long outrigger mounted on the rear of the helicopter called a tail boom, and attached to it a small propeller or tail rotor, rotating in a vertical plane parallel to the fuselage. This tail rotor is connected to the power plant by means of a long drive shaft. The pitch of the tail rotor blades may also be varied. Their degree of pitch is controlled by linkages to a pair of rudder pedals located in the pilot's compartment. When the tail rotor pitch is increased, the blades act like a conventional propeller and pull the helicopter's tail away from the direction in which the torque reaction tends to turn it. Or the pitch may be lessened to such a degree that the blades offer very little resistance, and thus allow the tail to be turned in the direction of the torque reaction. As we can readily see, this arrangement provides us with an excellent means of directional control. But now, let us continue our vertical ascent. Notice how the fuselage hangs like a pendulum, with its center of gravity directly under the rotor head. We are moving upward, but suppose we want to increase our rate of climb. All we do is increase the pitch on the main rotor blades and add throttle to maintain RPM. To slow down our vertical ascent, or to hover in midair, we lower the collective stick to lessen pitch, and at the same time maintain RPM by adjusting the throttle. We are hovering in midair, preferably 3 to 5 feet off the ground. So far we've demonstrated the first function of the helicopter, the function of vertical flight. Now we're ready to demonstrate the second function, that is, horizontal flight. Assuming there are no wind currents, our main rotor blades are turning in a disc plane that is horizontal, and the lift and thrust vectors are perpendicular to the disc. Movement in any other direction will be achieved by tilting the rotor disc in that direction. Logically, we would expect the helicopter to follow the absolute direction in which the disc is tilted. The force of gravity, however, is pulling the machine downward. At the same time, the rotor is pulling it upward and thrusting it forward. The resultant of these forces is forward motion. As forward motion begins, a loss of lift results due to the tilting forward of the lift vector to provide thrust. To maintain altitude, add collective pitch, making small throttle adjustments to maintain RPM. The method by which the rotor disc is tilted is called cyclic control. Situated directly in front of the pilot's seat, like the control stick of a fixed-wing aircraft, is the cyclic control stick, which actuates a series of linkages leading to the lower of 2 circular metal plates, one above the other and separated by bearings. This entire mechanism is called a swash plate. The lower plate does not revolve, but may be tilted in any direction by movement of the cyclic control stick in that direction. This movement forces a corresponding tilt on the upper plate, which revolves on the bearings at the same rate of speed as the rotor. The hub of the rotor blades in this particular machine is connected to the upper revolving plate by suitable linkages, which force the entire rotor disc to tilt in the direction first imposed by the movement of the control stick. Cyclic control is independent of collective pitch. Collective pitch changes may be applied regardless of the angle of tilt of the rotor disc. Generally speaking, the collective pitch of the blades provides vertical lift, while tilting the rotor provides forward, backward, or sideward motion. Let us assume then that we have tilted the rotor disc forward and are moving forward. As we do so, we notice a slight loss of altitude. This is due to the fact that while we are hovering just above the ground, our rotor was forcing air downward in a limited area, and thus building up additional air pressure beneath the helicopter. This additional pressure is referred to commonly as a ground cushion. When the helicopter moves forward, it slips off this ground cushion into thinner, less compressed air, and so suffers a slight loss of air support from below. The pilot, however, compensates for this loss by applying more power and by increasing the pitch of the main rotor blades. Before we've gone very far, however, we notice a tendency of the craft to regain this lost altitude. Additional lift, called translational lift, is imparted to the rotor by virtue of horizontal motion. So far, we have seen the first function of the helicopter, namely vertical flight, and its second function, horizontal flight. Now we're ready for its third function, namely directional control. This is managed by two simultaneous maneuvers: tilting of the rotor disc in the direction we wish to go, and changing the blade pitch of the tail rotor. Let's assume we want to make a right turn. Our cyclic stick is in the forward position. Now we press it slightly to the right. This tends to pull the craft slowly about in the direction the disc is tilted. Such a turn, without steering help from the tail rotor, would result in a slipping turn similar to the turn a fixed-wing aircraft would make using aileron and no rudder. So, at the same time that we apply cyclic stick, we gently add right rudder. This decreases the pitch of the tail rotor and allows the torque reaction from the engine to swing the tail to the left, turning the nose to the right. The helicopter then makes a coordinated turn, the way a fixed-wing aircraft does when ailerons and rudder are applied simultaneously. When the heading we want has been reached, we neutralize the controls and roll out of the turn. Reversing this procedure would naturally turn the helicopter to the left. Sideward flight of the helicopter to right or left can also be achieved simply by pitching the tail rotor blades through rudder pedal action, so that constant fuselage heading is maintained regardless of rotor tilt or fuselage movement. The question often rises, if a helicopter engine fails in midair, won't the helicopter immediately go into a free fall and crash? Fortunately, this need not happen. A helicopter, if handled properly, can glide to a landing more easily than can a fixed-wing craft, because it needs less space in which to land. Such a dead engine landing is called an auto-rotation landing. When the blades are being driven by the engine, they force the air downward through the rotor system. When the engine fails or is cut out manually, the helicopter itself begins to lose altitude. But the air passing upward through the rotor system forces the blades like a windmill to continue their rotation in the same direction they were going. As the helicopter goes into auto-rotation, the collective pitch stick must be put in full down position, reducing the pitch to a minimum in order to lessen drag, thereby permitting sufficient RPM to be built up. In fact, the RPM will generally be the same as when the machine is flying under power. As long as the rotor is turning at sufficient RPM, it is generating lift, powered or not. 20 or 25 feet above the ground, we flare out holding minimum pitch and return to level position. As the helicopter begins to settle and reaches about 10 feet of altitude, increase the collective pitch of the blades. By doing this, we turn the potential energy of the rotating blades into lift. A minimum of about 400 feet is required at zero airspeed to get the average helicopter into effective auto-rotation. That is, the plane should have at least 400 feet in which to make the transition from powered to auto-rotation flight. However, at cruising speeds of 30 miles per hour or more, effective auto-rotation may be entered into at much lower altitudes. Because the forward speed allows most of the 400 feet of air travel required to accomplish this transition to be done in horizontal rather than vertical flight. Another factor affecting flight that every helicopter pilot must become familiar with is density altitude. To explain it in broad terms, the gases that make up the air are composed of numerous molecules. The number of molecules is usually measured in terms of so many per unit volume. An increase in barometric pressure will pack a larger number of molecules into the same space and make the gases or the air more dense. An increase in temperature expands a gas so that a smaller number of molecules occupy the same space and makes the gas thinner or less dense. An increase in humidity decreases density by replacing heavier air molecules with lighter water vapor molecules. For purposes of illustration, picture a column of air existing over a certain field. If we set our altimeter at 29.92 inches of mercury, standard air pressure at sea level, our altimeter will indicate to us an altitude determined by the pressure of the air on the altimeter. This altitude is called pressure altitude. However, the performance of our helicopter is greatly affected by the density of the air through which our rotor blades are moving. To determine this density, we must take into account other atmospheric factors which affect air density, temperature, and humidity. An increase in temperature and a higher humidity will decrease the density of our air column. By taking into account these factors, we are able to arrive at density altitude. That is, pressure altitude corrected for temperature and humidity. The pilot must know the density altitude of the area in which he is flying his helicopter, because it will bear directly on the performance of his machine. The rotor blades develop more lift in dense air, and the engine develops more power than in thin air. The density altitude may get so high that operation of the helicopter no longer becomes practical unless certain precautions are taken. For example, loads must be lightened. The pilot must know that response to control changes will be slower and less predictable. For the sake of explaining basic rotary wing flight, we have chosen one particular type of helicopter for our demonstrations. This is not to deny that there are other and equally successful types or configurations. In heavier machines, capable of carrying up to 12 persons or more, 2 rotors instead of 1 may be used. Since the torque effect of either rotor can be offset by the other, no tail rotor is needed. Twin rotor machines like the Fokker design mentioned earlier may also mount their rotors side by side, although this type requires wider storage space than other types. Single rotor helicopters have been devised using jet propulsion applied at the tips of the blades to rotate them. This type too needs no tail rotor, since there is no engine torque reaction to work on the fuselage. All power originates at the tip of the blades. However, a rudder for directional control is mounted at the rear of the fuselage in the area of maximum rotor downwash. The number of blades on the individual rotor systems may vary from 2 to 5 or more. To conclude this brief introduction to rotary wing flight, let us summarize our investigation of the helicopter in terms of its 3 primary functions. The first of these is the function of vertical flight. The second, the function of horizontal flight. And finally, the function of directional control. All 3 of these functions are performed for the most part by the rotor system, the blades of which act as an airfoil revolving about a hub. When pitched at different angles of attack, they produce the necessary lift. The pitch of the blades is controlled in the following way. The pitch of the individual blades collectively is controlled by the collective stick at the side of the pilot seat. The collective pitch of the blades, supported by sufficient power from the engine, determines the speed at which the helicopter moves vertically. Horizontal flight is controlled primarily by the cyclic stick, which can tilt the plane of rotation of the main rotor in any desired direction. Direction of a tilt determines the direction of flight. Because of its unique versatility, its ability to climb vertically, to hang motionless, to move in any direction regardless of heading, the helicopter has opened up an entirely new realm of air operation. At present, it still lacks great speed and the power to lift heavy loads. But these developments will come with time. It is enough to know that for the present, today's helicopter has proved the ancient theory of rotary winged flight to be a practical one, as many men can testify.